Hey you guys, Lysandro here, and today I'm gonna do a tutorial video. I know it's late and everything, but usually I get my inspirations late at night. I guess a lot of people do and all. But anyway, I want to do like tutorial videos, kind of to do something beneficial for others and everything. Also, it's one of the things I'm really good at explaining and all. And today I'm gonna explain I'm gonna start with the basics and electricity. Okay. Now, I know a lot of us know what I know about electricity. We use it on our everyday devices, whether it's cell phones, tablets, or vehicles, or anything of the sort. Yeah, we, we use electricity or households, like power lines, things like that. Okay. And one of the most common things is a battery. Battery is known for storing electrical power. Let's see. But what is uh, electricity? What, okay, we all know the basic diagram of a circuit. This is a little light bulb. It's kind of crappy looking, but try to bear with me. I know. You connect a terminal negative and positive, and then you have electrical power and all through the circuit. But what really is going on? Uh, what really is going on here? Okay, like if you guys know what atoms are just basically made out of protons, neutrons, and electrons, which are basically your positive charge, which is this is a plus here. Positive charge, neutrals are neutral, they have no charge, zero electrical charge, and electrons is a negative charge. Okay, and what if I were to put an example of let's say a nuclei, let's say I have two protons here, two neutrons, which is constitute it doesn't constitute any charge, however it constitute mass and all. What you have here, this is just a nucleus. You often also see this as alpha particles, which alpha particles are essentially helium nuclei. You have you have you have your protons, which are two. That's your that's your atomic number. The same number of protons as your atomic number. You have your number of neutrons, which is your zero charge. You have two, and you have your electrons, negative, which you have none over here. Okay, and what happens here is that basically what you get is that you basically uh, you basically add the negative charges. Um, you basically add the negative charges to the positive charges. If y'all know negative numbers, y'all know that negative and positive numbers of equal amounts cancel out each other. So positive 2 plus 0, since we don't have any negative charges, you end up with a net charge of 2. Okay. Now, before I go any further, electricity is basically the electrical uh, potential between charges. Okay, and basically you have pos you have positive charges, this one right here, and negative charges, and they both attract each other. And that's and basically when we apply power to something, we're basically forcing charges to travel through the device by which we take advantage of the electrical potential, uh, which is the workload that's gonna go through the device, and it goes to the positive terminal. Okay, it if we were to just connect this, it would still go through. It would let's say if let's say we didn't have the any load on here. By load, I mean the device you're connecting to. Let's say you were just to connect the battery. Electrons are still gonna flow and everything. The thing is that if you do that, this would be a short. It's just will be a short. It will pretty much a lot of the electricity will dissipate in the form of heat. Every every conductor every conductor dissipates energy in the form of heat. Now, this differs when you go into superconductors, but that's a different deal now. Anyway, getting back to the atom and all. If you have the same nucleus, two protons, two neutrons, and let's say you have a shell. Shell are the orbitals that circle the nucleus, which together they constitute the atom. So you have two electrons here. So basically, what you get here is what you get here is you basically have the same two protons. You have the same two protons here. Let me make this more clear because that looks like a one. You have the same two protons. You have the same two neutrons. Sorry about that. You see two neutrons which are zero charge, and this time you have two electrons. Okay. Now, negative 2 plus positive 2, that's 0. So your net charge is 0. So your atom has 0 charge, so it's neutral. Okay. Now, if you go ahead and take this a little bit further, um, the same thing, two protons, um, two neutrons, and this time we'll have three electrons. Okay, so three electrons make a second orbital. Later on, I'll explain why I have two orbitals and all. Two different shells. Reality, these are shells. You have okay, you have three electrons. Um, so basically, you have two protons, two neutrons. Okay, you have this time you have three electrons. Okay, so mm, 2 plus negative 3, your total is negative 1. So you have a net charge of negative 1. So So basically, you have this right here. This is an example of a negative charge atom. This is a neutral atom, and up here, this one right here, this is a this is a positive charge atom. Now, um, if you were for some reason to put a conductor from this atom to this one, you would you will get an electrical current because of the electrons that would travel from uh, the this negative charge atom uh, to the positive charge atom. And if you get the net charge of each one of them, -1 plus uh, +2, you'll still have a positive charge of you still have a positive charge of 1. Okay, and that means um, it'll attract another electron, and that's basically what's going on here. You're getting uh, you're getting a current of electrons. When we apply electricity, we're basically taking advantage of the current and uh, work that goes through this circuit. Now, one thing I want to make clear is that I know this is a little bit too early to explain this, but there are two forms of electricity. You have your DC, um, you have your DC with direct current. Yeah, um, I really suck at using this, but direct current. Okay, okay, so you have your direct current. Okay, this is direct current. This is when you only have your currents only traveling in one direction. It's one directional. Now, and usually the schematic symbol is something like this. It's either this, sometimes they use this, but most commonly it's something like this. This is the schematic symbol for DC current. Okay. The other form of the other form um, is alternating current, AC current. Now, now direct current, that's usually what you get in batteries. AC current, on the other hand, is usually what you get from power outlets. Um, like for example, you draw 120 volts AC. It's a little different because to start off, here's the schematic symbol for AC current. It's a sinusoidal wave. If you don't know what a sine wave is, if you take in um, trigonometry, they'll cover sine waves. And basically, what the the difference between AC and DC current is that AC current is alternating. It's the current changes direction. Let me just create a circuit here. Okay, AC um, AC current has like what you call phases. Like one moment it can in a given time frame um it's there's negative to positive charges going in one direction. The current is going one direction, and then it alternates afterwards um, when it heads the other direction. So basically, when you look at your your cell phone charger, your wall adapter cell phone charger, if you look in the back, it'll give you something like 120 volts AC, 120 volts AC, and you'll see something that says 60 60 hertz. Okay, 60 hertz. It means that basically basically it alternates 60 times in a second. 60 times in a second. That means that let me let me create a sine wave. Okay, if you see here, you see that the current rises up to the peak. That's your amplitude. That's your amplitude. It rises up. This is your amplitude, often referred to as A. Okay, your peak is here, and this would be your typical one 120 volts. Okay, your time frame here, it's usually usually this is one cycle. This would be 1/60, 1/60 a second. Okay, 1/60 a second, because you have you have 60 cycles within 1 second. So that means that you're in one cycle, you have your current going incrementing. At this point, it'll get to a maximum of um, of 120. Then after a period of time, it'll start decrementing, and it'll reach zero. That's when you have no current. The current ceases. At this point, your current starts to go the other way, up until a point which you reaches your negative peak, which is negative 120. Okay, negative 120. Okay, once it reaches that peak, it, it starts going us back to zero, and then the whole process starts all over again. Another sine wave, another period. One thing I want to cover is that your frequency is equal to 1 over your time frame. Is 1 over your time frame. So basically what it's showing here is you is showing that your current is constantly changing back and forth with 60 times within a period of 1 second. Okay, so in theory, if um, if you were to touch this, if you were to touch this within these within the certain points where it reaches zero, you wouldn't get electrocuted. Of course, um, one 1/60th of a second is really fast, so there's no possible way you can touch a live AC wire without getting electrocuted. People normally aren't that fast to touch something like that. Now, one thing I want to make clear about AC electricity, AC power, is that while this one is normally is unidirectional, um, and it's normally has uh, has a constant what they call a magnetic flux. Every current has what you call a magnetic flux um, that's directional and that that circulates. In this case, this one's directional this way through the current. This will be your current, which is I. I stands for current, which is measured in amps, which is measured in amps. Okay. Now the thing about DC uh, DC current is that from the point it starts, you let's make a graph here. The point it starts is that your current goes, and this symbolizes your magnetic field. Your magnetic field starts at a point, and which the flux of the magnetic field um, increments, and once it reaches a certain level, it stays. And all. Of course, this isn't exactly how they graph it and all, but this is just for demonstration purposes and all. Um, your current is your current only changes once you start powering up, or uh, when it starts powering down. These are the only times you'll have these are the only times you'll have like electrical change. And the thing about electrical um, change in magnetic flux is that you can't um, you can't induce electricity. Now, the thing about AC is that since it's constantly changing, like it shows in this graph, you can induce current. You can induce current in a conductor, and that's where this whole deal with magnetic flux comes in. When you pass a changing, uh, a fluctuating magnetic field through a conductor, it generates an electrical field. Electrical fields and magnetic uh, fields are proportional to one another. Okay, and um, and that's where this comes in. You can induce a little bit of current with DC power, but you only generate it in the incrementing slope and the decrementing slope, which is you'll hardly get anything. And that's the thing about AC. You can induce power. You oftenly and you oftenly induce power in transformers, inductors, that sort of thing. I'll cover inductors later on and the tutorials, but basically AC is an AC is very important because AC is oftenly used in a lot of when it comes to like telecommunication, um, transformers, or a variety of different wireless technology. If you look at if you look at Wi-Fi, you look at like your cell phones. If you look at transformers or inductors or anything, or even the QI chargers that they have today in cell phones, all those have to do with AC. That's how they're able to send electrical signal. Your your electrical signal that you receive on your cell phone or your Wi-Fi internet, it's all AC. It's a sinusoidal wave that's constantly changing, alternating, you know. But this is just basic description of electricity. This is just the beginning part of it. On the next tutorial, I'm gonna be covering much more in-depth concepts in regard to like electrical circuits. But anyway, I guess this will be all for now, and I'll catch you guys next time. Bye.